not the same ratio as the previous problem, is it?
Why would it not be? Because that ratio is equal to big G, the constant, times the mass of the central object, the mass of the sun, over 4 pi squared. And the math people insist that pi and 4 are both constants. It is the exact same ratio. So if I asked you for Jupiter, what would the answer be?
Same thing.
Oh, what?
Weird.
Okay, so it's 3.39 times.
10 to the 18th meters cubed over second squared.
But we don't. Oh, never mind, because they're farther away.
It is farther away,
Yeah,
and the period's also longer.
yeah, I was thinking, like, we don't have the same exact
That
year.
makes sense, since they all like orbit around the sun and it's the center mass that matters.
Yes.
Okay.
So let's actually show that that's true, that I'm not just making stuff up and just seeing who's gonna come back later and say, hey, you lied to us.
You said it, not me.
Though there's actually been, I don't know how I could pull it off, but could I go an entire class making stuff completely up, all completely wrong, and see how long it takes for someone to challenge me?
And that class is today.
You could totally do that. I don't know if it'd be like ethical, like just telling people everything.
I'm not quite sure how I'd feel afterwards if no one ever challenged me if I'm just doing complete BS.
I think you'd be able to go for a while. I think, you know,
I'd
more
give
than
it-
you'd
I think
expect.
somebody would eventually catch on and be like, okay, this sounds weird.
I'd give it a half an hour tops.
Okay, well, I can live with a half hour.
Yeah.
An hour and 15 minutes tops, that I don't think I'd feel good after that one.
At the very end of class, someone's like, hey, this is all wrong. I knew it from the beginning.
So Earth, 1.5 times 10 to the 11th meters. The period of Earth, let's go to 365.3. I'm just going to use days. So let's figure out that new ratio here, since I'm using different units. So R cubed over T squared for Earth. So that cubed over that squared. And then for Mars. So what's the new ratio with the new units?
About 2.5 times 10 to the 28th meters cubed per days.
Yeah. I'm good with the units. Anyone else got the same number?
I did.
Yes, I did. All right. So what the claim is that this is going to be roughly the same value we get for Mars. And so 2.28 times 10 to the 11th cubed over 687.0 squared.
Will we not break that down into, oh, never mind. It's 2.5, yeah, times 10 to the 28th.
So we get the same value for Mars, even with elliptical orbits. And the same works for Pluto. You get roughly the same value for all the planets.
What about Pluto?
Pluto,
It's not a planet, so.
I was about to say,
Wow.
do we even count Pluto?
it's a planet in here.
Yeah.
Right.
But anything going around the sun, so that goes for all the little asteroids in the asteroid belt,
Yeah, yeah.
as well as planet Xena.
So, hold on. wouldn't that mean that Saturn, we'd have to account for its rings?
Well, I mean, the rings are traveling with the planet.
It's all still center mass.
Yeah, but
What would change with Saturn? What are you thinking?
I don't know, I'm just thinking of like how that would, it's not in the actual mass itself, but it has mass around it. So, I don't know, it'd be like the moon with Earth though. It doesn't
Yeah.
change anything.
Yeah, the primarily concerned with just the planet, the tiny little, the satellites of the satellites are traveling with it. Yeah, I'm not quite sure where I'm going with this, so I'm gonna stop.
You're good, I think I understand.
Now, this whole thing of this being equal to the same thing for all the planets, this is one of Kepler's laws. I think it's the first one. For whatever reason, I really have difficulty remembering which laws, which for Kepler. I think it's Kepler's first law. "40 years of Kepler's life was spent trying to come up with these relationships, and actually, based upon, he was looking at astronomical data, an amazing bit of deduction, and figuring out that this stuff holds true. I mean, figuring out the periods, imagine without satellites, without any probes that we send out into space, you're trying to figure out how long it takes for a planet to go around the sun, when all you basically see it's doing some little, figure 8 in the sky. He also had the idea that planets do travel in an ellipse, and the sun is at one of the foci. One of them. So, think about what an ellipse is, or what is an ellipse?
It's like a oval circle. You know
But
what I
how
mean?
is it different from an oval circle?
The distance to the center is not the same at all, the outside points.
Okay, that describes a lot of things.
Well, the,
But I guess that is how it's different from a circle.
the endpoints from the longitudinal are the same distance from the lateral, or not lateral, but the same distance. Sorry.
So if I've got an ellipse here, you're looking at the major and minor axes?
Yes.
Okay.
Those it's not an oval, and so that it's misshapen. It's kind of like symmetrical enough for us to find the radius of, or like the circumference of both minor and major axes.
Okay, I might nitpick some of the words, but there is indeed symmetry here. Let me sort of spoil some of this. If you take 2 points, any 2 points that are not the same.
Yeah.
So imagine you have a cork board here, you put 2 tacks into the board. You then take a piece of string and you let the piece of string sort of hang between them. You take a pencil or pen and you sort of stretch it out so that the string is tight. So if you look at this distance here, plus that distance there, there's a lot of points which will have that exact same sum of distances, that plus that, there's a lot of points. So there's a point over here, which it's closer to this one, but farther from that one, but the sum of those 2 distances is the same. So if you map out all the points which have that same sum of distances, that's an ellipse. These 2 tacks right here are the foci, or singular focus. Kepler figured out the sun's at the focus, at one of the foci, or at a focus, and the Earth starts traveling around. And the last thing Kepler figured out, so if I have my sun here, is that the Earth is not traveling at the same speed the entire time. Because the force, well, let's do the Kepler thing and then we'll talk about reasons why. So what he did figure out though is that if we look at how far the Earth travels in, let's just say a month. So in 1 month, the Earth travels from here to here in 1 month. And this area here has some value. It's kind of like, looks kind of like a triangle. There's a small arc to it, but there is a shape that has an area. What he figured out is that in the same amount of time, it sweeps out the exact same amount of area. So when it's closer to the sun, it's going to be traveling faster, so that this area, if that's 1 month, that area and that area are the same. Equal areas in equal time. And again, all this from just looking at, I think primarily the data from Tycho Brahe. Didn't even believe the sun was at the center.
So
But Brahe had incredibly detailed astronomical data.
wouldn't that mean that the ellipses doesn't matter in this case? Because the months are all gonna be the same, it's gonna be the same time no matter what.
If,
You get what I'm saying?
no, I'm missing it.
So what I'm saying is it doesn't matter whether it's a circle or an ellipses because the time, the period is all the same. Since it takes a month for it to get past that distance at the top right, but it still takes the same amount of time in the bottom left.
But this is a greater distance along here.
Oh, okay,
In other words, the Earth speeds up when it's closer to the sun.
okay.
Doesn't the period always reference the full,
Yes, it does. The full orbit is one period in terms of what a period is usually, how it's usually used. But for whatever other time frame, we can pick how far does the Earth travel in 1 second, in 1 day, in 30 days. And I probably should have gone with days instead of months here, but since not all our months are the same length. But assuming that these have the exact same length of time, that the planet is going to travel faster closer to the sun.
could I ask another question? What is the other focus in these ellipses and?
Oh, what's over here?
Yeah, is it just, no one knows? Are they all different for every planet?
I don't think they are, but I don't know for sure.
Wouldn't they be? Because the ellipsis would be like longer for each further planet. So the focus, it has to be shifted with each.
Right.
With each
No, the focus is still pretty much the same. It doesn't, I mean, it's farther out, so
Yeah, so since the focus is here, doesn't there have to be some sort of like equidistance from the focus to the end on both sides?
you're talking the same distance, what, from here to here?
No, from there, from focus 1 to the closest edge and focus 2 to its closest edge.
Oh, yes, yes.
Yeah, so if your whole orbit is longer, then your focus has to be
Yeah.
pushed further, so it has the same distance from the edge as the sun.
All right, so if I'm understanding what you're saying, I would disagree. All right, so that's a focus and exaggerating. We'll just say that's the ellipse right there.
Yeah,
That's
sure.
one planet's orbit. So that distance would be the same as that one.
Yeah.
So you're saying that,
If the whole ellipsis was larger.
that distance could still be the same as that distance.
Yeah, if it changes the same amount in the same direction.
Yeah.
Don't they not change the same amount in each direction? I could be totally wrong, but I thought the orbits were like when they're all lined up, they're closer on one side and further on the other. I'm trying to picture like
All right, so how close these are to a circle versus, I guess being completely squatted or flattened is referred to the eccentricity of the ellipse. And the eccentricity of the orbits are not all the same. Some orbits are closer to a circle and some are farther out. Pluto, I think, is the worst offender in terms of it's the most eccentric of the orbits. To the point where sometime in the 90s, Pluto was actually the 8th planet.
What?
Pluto was closer to the sun than Neptune
Oh.
for about a 6-year period in the 90s.
That's
And
why
to
they-
punish it, it stopped being a planet.
Yeah, I was about to say that's why they don't like it.
So, whatever the elliptical orbit is that the planet is doing, the sun is at the focus. Now, so it is also possible that the orbit is like that, where that's still the focus of the ellipse. So it's not that Yeah, so I guess the other focus doesn't have to necessarily be in the same spot. It could be, I don't think it is, but there's nothing in what I've done here that would indicate that it has to be different. All right, did I address your comment?
Yeah, yeah, there's just some amount left up in the air still.
All right, let me hit another topic and then feel free to ask questions again.
I might just do some Googling.
So if we think about it from a Newtonian point of view, the Earth is accelerating at this point right here. The Earth is accelerating towards the sun. That's the force. The acceleration has to be in the same direction as the force. The Earth is traveling in this direction. So that's my velocity and that's my acceleration. So my acceleration is not perpendicular to the velocity, so it's not all centripetal acceleration. Some of the acceleration is centripetal. So if we break acceleration up into components, let's see if that'll work. We have a component in this direction that's perpendicular to the velocity. That's centripetal acceleration. And then there's a component that is in the same direction as the velocity at this point, the way I've drawn it. And this is just what we generally call acceleration or tangential acceleration. So this is the acceleration which changes the speed. This is the acceleration which changes the direction. So since the acceleration is in the same direction as the velocity, the Earth is going to speed up. And the Earth is going to get faster and faster, and then once it passes this point, it's going to start slowing down. At this point, it's at its slowest, and then it'll start speeding up again. And so we have a physics explanation for why it speeds up as it gets closer and then slows down as it goes away.
The tangential acceleration starts to line up with the centripetal acceleration, right?
No, tangential will always be perpendicular.
Well, that's.
At this point right here, there is no tangential acceleration, it's all centripetal.
Okay.
And the same with right there.
Well, the mass is gonna pull on it differently.
Say it again?
The mass is gonna pull on it. Once you get closer to something, don't you have like different gravity?
Yeah, there's a
constants?
gravitational pull here.
Yeah. Wouldn't it be different from the gravitational pull above, like, top right? You know what I'm saying?
Above, top
So
right,
as
out
it's,
here?
as it's farther away from the planet, it has less gravitational pull, which is why it will take it longer, other than the force of gravity. So I think I answered my own question.
Okay, good.
I'm confused about something now.
Yeah.
Are we talking about circles right now? Or
No,
are we-
ellipses.
Okay, so then I'm confused about why the tangential acceleration is always perpendicular to the centripetal acceleration.
Because whenever you have a curve, so the velocity is always tangent to the curve. So the velocity would be in that direction.
Yeah.
Tangential acceleration, it's called tangential for a reason, because it's tangent to the curve.
I think I realize now, I just
Okay.
sort of was confused by the picture that was drawn, so.
My artwork did not speak 1,000 words.
It was just the centripetal acceleration isn't actually pointing at the sun. It's sort
Oh,
of
yeah,
like-
it's
like-
not. Yeah, not necessarily.
Would the, direction of acceleration and the centripetal acceleration be equal to each other? I mean, it seems like they would be equal at the two ends of the ellipses, would they also be equivalent to each other at, like when I'm doing it in my head, I'm seeing them being the same in other places along the ellipse.
So if I were right here,
Screw that.
the total acceleration would be in that direction, because total acceleration has to be in the direction of the total force. There'd be a component that's tangential and a component that's centripetal.
Yeah.
Sorry, I said that backwards. There's a component that's centripetal and a component that's tangential.
Right, but would the centripetal part and the direction of acceleration be equal to each other in certain parts of the ellipse? Like maybe-
Those two right there,
Yeah, yeah, yeah.
at this point and at that point.
Just those 2 points.
Yeah.
Or tangential, did I say it right?
Tangential.
Tangential acceleration and,
Centripetal?
yeah, centripetal acceleration, are they always gonna be perpendicular to each other?
Yes.
Alright, I think,
Assuming that the exception would be if one of them is equal to 0.
I think I do have a question.
Okay.
So our big G, which was the gravitational constant,
Right.
it stays the same.
Right.
We don't have any distance anywhere in our equation to figure out the speed or the mass of our object. So where does gravitational pull come into play? Because the orbit of the Earth, like when you get into a certain distance from the Earth, you're gonna have a different amount of orbit. You know what I mean? You're gonna have a different amount of gravitational pull. So
Okay, yep.
why does that not come into play when it comes into the ellipses where we have different gravitational pulls as we're farther away than we are closer? I know it speeds up, but wouldn't that also be a cause of the gravitational pull?
Speeding up.
Speeding up, like the orbit of it speeds up. You said it takes the exact same time for 1 month to pass out as it's farther away, but it also takes the same amount of time as it's closer.
Right.
Its speed changes, but the
Alright, so I'm gonna do a scattershot approach. I'm not 100% sure
Yeah.
of what your question really is. I
Like,
apologize for that.
I guess what I'm saying is, why doesn't gravitational pull play anything? Because we've got big G, which is a constant, but if it stays the same, then, you know, that would just mean that we're contradicting ourselves by saying that satellites orbit differently in the space.
Alright, is it? No, you're losing me here. Are you having a conflict with the fact that we had r cubed over t squared is equal to some constant?